Hi everyone, welcome to our PHP project on audio signal filtering. As you can see in the screen, our first critical step is sampling. We use the media code to read our raw analog audio file and successfully converted this continuous time signal into digital discrete signal. Now our signal is ready for filtering.
In this section, I will walk through the DTFT and frequency spectrum analysis. The main objective here is to project the time domain audio data onto a complex exponential device, allowing us to uncover the hidden frequency components. To achieve this, I utilize the MATLAB's FFT function. Now, because the spectrum of a real-valued digital signal is perfectly symmetric, we only need the first half of the data. To ensure our code runs flawlessly without any warning, we apply the floor function for n over 2 and successfully map the remaining points into a physical frequency vector in Hertz. From plot, we can see why the transformation is so crucial. It translates those messy time domain reports into a clear and visible spectrum. We can easily identify our useful audio signal at the lower frequencies and the broadband noise at higher ends. This clearly separation gives us the exact parameters we need for our next step, filter design.
For my section on FIR filter design, our sampling rate is 8000 Hz. This means our maximum frequency limit is 4000 Hz. From our spectrum graph, we found a high frequency noise above 12,000 Hz and a sharp whistle exactly at 800 Hz. Since natural human voice stay below 11,000 Hz, we set our low pass filter to 1200 Hz. This keeps the voice clear while blocking the high frequency noise. To remove 800 Hz whistle without hurting the noise, we added a notch filter from 760 to 860 Hz. Next, let's look at the windowing method. An ideal filter is infinite. If we simply cut it using a rectangular windows, it causes a Gibbs phenomenon, which leaves it too much background noise. To fix it, we use a Hamming windows. If you look at our impulse response graph, the Hamming windows move bring an edge to 0. Also, the graph is perfectly symmetrical, which proves it is a stable type 1 FIR filter. Moving to our frequency response graph, you can see the result. The Hamming window gives us a deep stop band attenuated of minus 53 decibels. This means the noise is successfully removed. Below it, the phase plot shows a straight linear line. This is very common. It prevents phase disturbance, keeping the speaker voice sounding completely natural. Finally, we choose a high filter order of 300. This gives us a very steep cutoff, but it costs a delay of 150 samples. Since we are processing a pre-recorded audio file offline, this time delay doesn't matter. We gladly accept this delay to get the cleanest possible audio output.
Next is about the bilinear transformation used in the design of the IIR filter. So based on the FFT analysis from the previous section, we identified two types of unwanted noise. A narrow tonal noise appears around 800 Hz, while additional high frequency noise exists above approximately 1.5 kHz. So to remove these noises, we designed two Butterworth IIR filters. The first is a bandstop filter from 760 to 860 Hz, and the second is a low-pass filter with a cutoff frequency of 1500 Hz. So the Butter function internally performs the bilinear transformation, which converts an analog Butterworth prototype from the S-plane into a digital filter in the Z-plane. This process generates the filter coefficients B and A, which are then used to implement the filter. Next is the first frequency response, showing the bandstop filter. The notch around 800 Hz removes the unwanted tonal noise while preserving the surrounding frequencies. And then we have the second frequency response, shows the low-pass filter, which attenuates frequencies above 1.5 kHz to reduce the remaining high-frequency noise. Next, we filter the stability using the pole zero plots. For both filters, all poles are located inside the unit circle, which means the ROC includes the unit circle confirming that both digital filters are stable. This stability is also verified mathematically by checking that the magnitude of every pole is less than 1. So overall, the bilinear transformation allows us to design stable digital IIR filters that remove both the tonal interference and high frequency noise.
Okay, although we successfully remove the noise from audio design, we do the sampling, DTFT, and windowing method for FIR filter design, and also bilinear transformation for IR filter design and also the calculations. So now let's to listen the original sound and the sound after we filter it. Original sound,
0125.
FIR filter sound.
0125.
And IIR filter sound.
0125.
Okay, so you can observe that the background noise has been removed.